Good days everyone, we are from Group 7 and now we are gonna to talk about photochemical reaction. So, what is photochemical reaction? This is the chemical reaction that need energy from light to occur. As we learned before, light is a form of energy, hence it will provide the necessary activation energy for the reaction to take place. There are few examples like which ultraviolet light, UV and visible light. As we learned it before, photon is the basic unit of light, thus the molecule absorbing the light will lead the molecule to experience a temporary excited state. So looking at the yellow figure 1, the molecule M in the ground state absorbs a photon, which will lead the molecule M to experience a temporary excited state. The molecule M star means that the molecule M in the excited state due to the absorption of photon. The next is example of photochemical reaction. The first example is the photosynthesis reaction. Sunlight is the UV which will provide the energy for this endothermic reaction. The second example is the human formation of vitamin D3 by exposures to sunlight. Vitamin D3 is a very special vitamin because it is the sunshine vitamin. The sunlight will give the energy for the cholesterol to synthesize the vitamin D3.
And now we would like to discuss two laws. One of it is Photochemical law. Photochemical law says that only absorbed radiation would be effective in produce a photochemical change. So even if you have a large intensity of incident light, they will not produce a photochemical effect if none of it is absorbed. See a simple illustration for effective absorption. So we can see that when a light falls off a body, which is the I node there, a part of it is reflected. So if IR there, a part of it is transmitted, and only a part of it is remain unabsorbed. So it is only the absorbed light is effective in bringing out a photochemical reaction. We will discuss Stark and Thin law of photochemical equivalence. This law states that for each photon absorbed, one molecule undergoes the photochemical process, but there is an exception. With a high intensity laser light, a molecule can absorb several photons in a single photochemical process. So, in this situation, the Stark and Thin law is not suitable to apply on it. You can see there is a picture about the illustration of the law of photochemical equivalence. You can see that one photon is absorbed by a random molecule, then it gets to achieve the excited state, then only it can become a product. So we can conclude that every atom or molecule that takes part in a photochemical reaction absorbs one content of radiation through which the substance is exposed.
I'm going to talk about the red law of photochemical reaction. First of all, I will start to explain from the chain reaction mechanism for a better understanding in the red law of photochemical reaction. Let's assume a chain reaction in the gas phase reaction, which is H2 plus Br2 to 2HBr. The empirical red law for this reaction is this. So why and how we get this empirical red law? For this reaction H2 plus Br2 to 2HBr, the accepted mechanism for the forward reaction is this, a three-step mechanism. For this mechanism, we write the differential equations for the time derivative of the concentration of H2, Br, and H. Note that the H and Br are the chain carriers. Now for this, the differential equation for the time derivative of the concentration of H2, where the dH2 over dt is equal to minus K2 BrH2 plus K2 prime HBrH. And for the Br, the dBr over dt is equal to 2K1 Br2 minus K2 BrH2 plus K3 HBr2 plus K2 prime HBrH minus 2K1 prime Br power 2. And last for the H, the dH over dt equals to K2 BrH2 minus K2 prime HBrH minus K3 HBr2. We choose the H2 to specify the rate of the overall reaction. This is because H2 occurs in only one elementary step, and it gives a simpler differential equation. And now we change the sign of dH2 over dt to minus dH2 over dt so that we can simplify the equation easier later. And next, we apply the steady state approximation and set the time derivative of the concentration of the chain carriers equals to 0. The time derivative of the concentration of the chain carriers, which is Br and H, are equals to 0. So dBr over dt is now equal to 0, and the dH over dt is also equals to 0. So now we can simplify the equations based on minus dH2 over dt and dH over dt. We found that these two, they are actually the same. So we can replace the K2 BRH2 minus K2 prime HBRH with minus dH2 over dt. And finally, we get dH minus dH2 over dt equals to K3 HBr2, which is the rate of the overall reaction. However, the H is one of the chain carrier, so we need to solve it. From the differential of intermediate H, we get the expression for the H, where the H is equal to K2 BRH2 over K2 prime HBr plus K3 BR2. Since Br is also one of the chain carrier, we need to continue to solve it. From the first step of mechanism, the reversible reaction, the rate forward is equal to the rate backward. So the Kf is equal to Kb, where K1 Br2 equals to K1 prime Br power 2. So K1 Br2 minus K1 prime Br power 2 equals to 0. And now we get the expression for Br, where the Br equals to K1 over K1 prime power 1 over 2 times Br2 power 1 over 2. So now we can substitute the Br into the H. And now we get the H is equal to this. Next, we can substitute the H into the rate of the overall reaction. And after the substitution of H, we get this. The whole equation is now divided by K3 Br2, and finally we get this equation. The empirical parameters Ka equals to K2 times K1 over K1 prime power 1 over 2, and Kb is equal to K2 prime over K3. So now we can substitute the Ka and Kb into the equation, and finally we reproduce the empirical rate law. So now we can look at the photochemical reaction. Same reaction, H2 plus Br2 to 2HBr. In photochemical reaction, the initiation step requires 190 kJ per mole to break the Br-Br bond, and this energy can be supplied by the ultraviolet light. So we look at the mechanism of photochemical reaction. The initiation step, the Br2 requires the energy supplied by the UV light to break the Br-Br bond and produce 2Br. So earlier in the chain reaction, we get dBr over dt equals to this. Now, in photochemical reaction, due to the absorption of the UV light, we let the J be the average rate of absorption of light, which measured in insights per unit volume per second. The rate of photochemical production of Br atoms in the initiation step is equal to 2J, so the equation for Br atoms is now equals to this, where the 2K1Br2 is replaced with the 2J. So from the first step of mechanism, earlier in the chain reaction mechanism, K1Br2 minus K1 prime Br power 2 is equal to 0, and we get the rate law is this. And now in the photochemical reaction, the J minus K1 prime Br power 2 equals to 0. So the rate law of photochemical reaction equals to this. The K1 Br2 is replaced by the J. So we get the rate law for photochemical reaction.
Finally, it is the exercise time. Here is the question. Let's check your answer.
And thank you.